Hello, you're very welcome to this video on natural logarithms. This video is a follow-on to an earlier one called logging into the powers that was based on the number base 10. This video is for first year students at DKIT Dundalk, and I'm Seamus Ballieu, and we'll make a start. So this video is about the number e, which is 2.718281828. That regular pattern doesn't continue, and the natural logarithm. So the base e is the base for this natural logarithm, and the abbreviation is ln, comes from the Latin name as you see there. So L for L and N for the natural, and it's a number like pi. So we're going to look at the derivation of the e, or some of the applications of it. And e is to do with growth. So we could look at an interest model just to get a feel for where the number e comes from. So supposing we deposit 100 cents in the bank at the start of the year, and we get 100% interest at the end of the year, so we get another 100 back, so that gives us 200 cents or €2. But what would happen if we got interest twice a year at 50%? So again, you see, at the end of June, if we got 50 cents on our 100 cents, and then at the end of December, we would get 75 based on the 150 from June, and that would give us 225 cents or €2.25. Looking at it 4 times a year, we have €100, 25 cents at the end of March, add on another 31 cents at the end of June, 39 cents at the end of September, and 49 cents at the end of December. We're effectively getting 25% each time, 25% of the amount that's in the bank. So gaining 25% interest 4 times a year gives us €2.44. And we keep repeating that process over different periods of time. So summarizing where we're at, if we deposit, if we put in the euro and get 100% once a year, the formula is 1 plus 1 over 1 to the power of 1, and that's equal to 2. But if we do it twice a year at 50%, so it's 1 plus a half, which is the 50%, to the power of 2, twice a year, gives us €2.25. If we do it 4 times, we get 1 plus a quarter, which is the 25%, to the power of 4, which is 4 times a year, we get €2.44. If we do it monthly, or 12 times a year, we get 1 plus 1 over 12, that's the interest, 8.33%. 12 times a year, we get €2.61. So you can kind of see these numbers are going to approach the E number. Looking at it weekly, 52 times a year, same process again, and the number tends towards €2.69. Doing it daily, each day during the year, so we get 1 plus 1 over 364 to the power of 364 equals 2.71, and that number is approaching E. And we could repeat this process continuously over each second during the year, and it would still approach 2.718, which is the E number. Again, E can be derived from various series. So this one that we've shown here is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on in an infinite series. So just to remind you that these factorial numbers in the bottom there, 4 factorial is 4 by 3 by 2 by 1, which is 24. 3 factorial, 3 by 2 by 1, which is 6. 2 factorial, 2 by 1, which is 2. 1 factorial is 1. And 0 factorial is also 1. And that's kind of related to, for example, 10 to the power of 0 equals 1. So summing up all these terms on the infinite series will give us the E number again. So just looking at it in detail, even if we add up the first 6 or 7 terms, we get 2.71. But if we add on the infinite terms, it eventually tends towards this number here. So E is 2.718281828, but the next digit doesn't adhere to that pattern. The next digit is 4. So there's an E button on the calculator, or it's the ln, and then it's usually the E is the second function on it. You do e to the power of 1, and you get 2.718, and so on. So natural logarithms, like we said on the logs to the base 10, is to do with powers. So for example, e to the power of 3 is 20.086, e to the power of 4 is 54.598, and if we asked the question, e to the power of something equals 40, well, we know by looking at this here that the power must lie between 3 and 4. So we'll come back to this question in a moment. But let's just look at this statement here. E to the power of 3 equals 20.086. So there's the power statement. E to the power of 3 is 20.086. But log to the base e of 20 gives us back the power, which is 3. And this is what we call a logarithmic statement. So the natural logarithm is the power to which e the base must be raised in order to get 20.086. So coming back to the question that we had, it's e to the power of 3.689 equals 40. So again, repeating the definition of the natural logarithm, the power to which e the base must be raised in order to get 40 this time, and the answer is 3.689. So e is the base, and the log to the base e of 40 equals, sometimes we don't need to write the bracket if it's a number just like that, and that's equal to 3.689. However, the symbol for the log to the base e can be encapsulated in this symbol here called the natural logarithm. The ln button on the calculator is already to the base e, so there's no need for us to write base e anymore. We're going to write it as the ln of 40, so it's understood that that means log to the base e. So the ln of 40 is 3.689. In other words, that's the power that's on the e. E to the power of 3.689 is equal to 40. So looking at this slide here, we're going to combine the exponential power, the e number, with the ln function. So if we take e to the power of 2, e to the power of 2 is equal to 7.3891. But if we take the ln of e to the power of 2, we see that's equal to the ln of 7.3891, and that's equal to 2. And that makes sense because we said that the log returns a power, so the ln of e to the power of 2 returns the power, which is just 2. So likewise for these here, the ln of e to the power of 2.4 would just return the power itself, which is 2.46. And even though the calculator gives an error when you try to calculate e to the power of 987, that's too large of a number for the calculator to do it. But we know that the ln of e to the power of 987 is the same as 987. So what do we notice? Basically, if we take any power of t, the ln of e to the power of t is equal to t. So effectively, the ln cancels out the e to the power of function, or the ln is the inverse function of e to the power of. So this was similar to what we said in the log to the base 10 and 10 to the power of. They're inverses of each other. So the ln will tend to cancel out the e and just give you back the power of t. So we're going to solve a logarithmic equation now in the natural log. So e to the power of t is equal to 105. So we take the ln of both sides because we know that ln of e to the power of t just returns the power t. So effectively on the left hand side, taking the ln of the left hand side, we get t equals the ln of 105, which is 4.654. So that's the power that's on the e that gives you 105. So here's a practical application. Suppose we have the temperature of a hot rod placed under running water that gradually cools down the heat, and the formula is given as T equals 12 plus 60e to the minus 0.4 T, where T is the time in minutes, and the large T, capital T, is the temperature in degrees Celsius. So we're going to ask a few basic questions. Part A, what is the initial temperature at time 0? Temperature after 5.6 minutes. Part C, if we can hold the rod when the temperature is 15 degrees Celsius, how long will it take to cool to this temperature? And what's the temperature after a long time? So looking at part A, what is the initial temperature? So T equals 0. So we substitute 0 in for T, just like we've done here. And that's 12 plus 60 e to the 0. So calculating that in the calculator, it'll return 72. But you can see that e to the 0, any number apart from 0, e to the power of 0 is equal to 1. 1 by 60 is 60, plus 12 is 72 degrees Celsius. So the initial temperature is 72 degrees Celsius. After 5.6 minutes, what will the temperature be? Substituting in 5.6, we get T equals 12 plus 60 e to the minus 0.4 times 5.6, and that's equal to 18.39 degrees Celsius. So the temperature has cooled down over the space of the 5.6 minutes, from 72 degrees Celsius to 18.39 degrees Celsius. So most of the modern calculators, when you put in the formulas, put in the numbers into that formula there, it raises the power and it keeps all this up in the power. So you just need to make sure that all that data is up in the power, that's e to the power of all that, to ensure that you get the correct answer on the calculator. Now, returning to the question then, if you can hold the rod when it's 15 degrees Celsius, how long does it take to cool to 15 degrees Celsius? So put 15 in for large T. So 15 is equal to 12 plus 60 e to the minus 0.4 T. So you can see that we're going to take 12 away from both sides of that equation. And that results in 3 equals 60 e to the minus 0.4 T. So next step will be, we'll divide both sides by 60. So doing that, 3 divided by 60 gives us 1 e to the minus 0.4 t, or just simply e to the minus 0.4 t. And now in the next step, it's like solving the logarithmic equation that we had a few minutes ago. We'll take the ln of both sides, and the ln will cancel out the e on the right hand side this time. So taking the ln of both sides, the ln of 0.05 equals the power there, minus 0.4 t. The ln is minus 2.996 equals minus 0.4 t. And now dividing both sides by minus 0.4, minus gives a plus. And effectively, t is equal to 7.49 minutes. And what's the temperature of the rod after a long time if we let the water run for a long period of time? So that's kind of an open question. We know that e to the power of a large number is very large. But here, if you put t in after a long time, e to the minus of a large number is going to be very small, because effectively e to the power of minus a large number, minus something to the power means it's 1 divided by e to the power of a large number. So 1 divided by a large number effectively gives us a very small number, which tends towards 0. So after a long time, the temperature is very small, very negligible value, close to 12. So you could even check out at 50 minutes in this case here, and substituting it in, we get that it's t equals 12 plus a very small quantity. So effectively, after a long time, the temperature is 12 degrees Celsius, because this bit here tends towards 0. E to the power of minus a large number is negligible, and 60 by negligible number is still small, so we can ignore that. So after a long time, the temperature becomes 12 degrees Celsius. In the current pandemic, the growth of the virus, it's well rehearsed on radio bulletins, and the formula follows something like this. You're familiar with the R0 figure, and it also follows an exponential pattern. You often hear about the exponential growth. So we'll come back to this in the next video on applications. So on the last video, the previous one, where we talked about logging into the powers to the base 10, we saw that the graph of I equals 10 to the power of t was a sharply increasing graph like this. And say if the time was 1, the current was 10. After 2 seconds, it was 10 to the power of 2, which was 100. After 3 seconds, it was 10 to the power of 3, which was 1000. So this graph is rising very quickly. In a similar way, I equals e to the power of t is an exponentially increasing graph. And here it is here, not as sharp as 10 to the power of t, but nevertheless, it is exponentially increasing, as you see there. E to the power of 0 is equal to 1. E to the power of 1 is 2.718. So there's 1. E to the power of 1, you can hardly see there on the axis. E to the power of 2 is 7.39. E to the power of 3, 20.089. So there's t equals 3. E to the power of t is equal to 20. And e to the power of 4, there's 4. E to the power of 4 is your 54. So looking at that graph in closer context to the 0, you can see e to the power of 0 is now the 1, e to the power of 1, 2.718, and so on. And e to the power of negative values tend to get very small as the number gets more negative. Now, the interesting question we could raise is, what's the slope on this exponential graph at any value t? So if we look at the value for 1, for example, if t is equal to 1, so looking at the slope of that green line that we've drawn there, and if we just draw a little triangle underneath there like that, if we go from 1 to 2, so if the run is 1, 2 minus 1 gives us the run, and just looking visually at the graph, that height there looks roughly somewhere between 5.5 and 2.72, which is 2.78. So roughly the slope of that green line is 2.78 divided by 1, so the slope is equal to 2.78. So we're kind of estimating the slope to be 2.78. But in actual fact, if we got into the detail of it and calculated, the slope is actually 2.718, which is equal to e to the power of 1. So this exponential graph has a unique property that no matter what t value you pick along here, supposing we pick the time equals 2, and we drew the slope on that graph at t equals 2, the value on the slope of the line at t equals 2 is the same value as e to the 2, as we saw when t was equal to 1, the slope of the line was the same value as the current. I was equal to e to the power of 1, 2.718, and the slope of the line was also 2.718. And in actual fact, there's a third property associated with this. So not alone can you calculate the value of the function at particular t values, it also has the same value when you do the slope. But if you take the area under the graph to the left of it, it also has the same area, 2.718. And just to do a kind of an estimate by looking at that graph there, so the area inside that rectangle from 0 to 1 up to 2.718 is E, but we're sort of saying that roughly that area above the graph underneath there is equivalent to that area there. So effectively, if you pick a t value, for example, t equals 1, the value of the function is e to the 1, but the slope of the line is also e to the 1, and the area to the left is also equal to e to the power 1, which is 2.718. So that sort of thing is to do with the growth, and we'll see later on that this function is related to properties of growth. So here's the graph of the ln of t. So it's rising less steeply than the exponential graph. Again, seeing the values, the ln of 1 is equal to 0 because e to the 0 is equal to 1. The ln of 2 is equal to 0.69 because e to the power of 0.69 is equal to 2, and so on. And as we saw when we were doing the log to the base 10, I equals 10 to the power of t, and the opposite function I equals the log of t, log to the base 10, we have here that I equals e to the t and I equals the ln of t are inverse functions of each other. So here's the graph of I equals e to the t, here's the graph of I equals the ln of t, and here's the line I equals t. So there's a symmetric relationship between both functions in an axial symmetry or reflection about that line. So if we pick this point here on the I equals e to the t graph, the t value is 1.2 and the I value is 3.3. But if we reflect it about the line, the coordinates get flipped around so that the t value is 3.3 and the log of t becomes 1.2. So this is related to two statements that we mentioned earlier on. Here's the power statement. E to the power of 1.2 is equal to 3.3, but the ln of 3.33 gives you back the power, which is 1.2. So this is a power statement here. This is a logarithmic statement. So the logarithmic statement is linked to the log function, and the power statement is linked to the exponential function. So we're going to take a wee look at powers, some of the rules associated with the powers to the base e. So these are going to be similar to what we did in log to the base 10. So we have e to the power of a by e to the b, the same as e to the a plus b. So e to the 3 by e to the 4 is e to the 3 plus 4, which is equal to e to the 7. E to the a divided by e to the b is e to the a minus b. Likewise, in the equivalent sense in the logarithmic, the ln, or the log to the base e of ab, is the ln of a plus the ln of b. So just looking at some numbers, for example, the ln of 12 is the same as the ln of 3 times 4, which is the same as the ln of 3 plus the ln of 4. So taking those numbers then, we get 2.49 is equal to the ln of 3, which is 1.1, plus the ln of 4, 1.39, and that's to do with the powers. So we can do a little proof on that. So we're trying to prove that the ln of AB equals the ln of A plus the ln of B. So if we let the ln of A equal x, the ln of B equals y. So x and y are essentially powers because the log or the ln return powers. So therefore the base, which we know is e to the power of x is equal to a, e to the power of y equals b. So if we multiply these two equations here, so the left hand side gives us e to the x times e to the y, which we know is equal to e to the x plus y, and that's equal to ab. Now, taking the ln of both sides of this latter equation here, so if you take the ln of e to the power of x plus y, it returns the power x plus y equals the ln of ab. But we know that we already have x, y here that was given to us at the beginning. X plus y equals the ln of a plus the ln of b. So just equating both of those now, we can see that the ln of ab is equal to the ln of a plus the ln of b. So all the properties that hold for log to the base 10 also hold to base e. So we conclude the video at this point, and we'll have some applications then in part 2. So thank you very much.